Good evening and welcome to the Exploratorium this evening and to Everything Matters, Tales from the Periodic Table. Tonight we are doing the element selenium. Now I hope that you all have your collectible card with you. This will tell you not everything you need to know about selenium, but it's a really nice collectible card. And if you had been here for the last 33 months, you could have collected the entire set from starting at hydrogen, which is where we first began, and last month to arsenic. And we add the new element, selenium, this month. Who's been to After Dark before? Wow, okay, so we have a really good crowd here who knows After Dark. Tonight, again, we're going to talk about selenium. I expect this will last 30 or 40 minutes. I never know because I've never done it before, so hopefully we'll get this going real soon. So, selenium is found right there on the periodic table. It is element number 34. 34 is its atomic number. It's how many protons are in the nucleus of the atom. It has variable number of neutrons in the nucleus, which we'll talk about in a little bit. And it was discovered a good long time ago. It was discovered by these two fellows simultaneously but separately, Johann Gottlieb Gahn and Jan Jacob Berzelius. And they both discovered it in 1817. They noticed that it was similar to another element that had just been discovered, one called Tellurium. Tellurium is actually named after the Earth. Tellurium kind of looks like this. It's similar to selenium. They discovered selenium in the kind of the tailings of refining elements from pyrite. Pyrite is iron sulfide, but selenium is an impurity in that. And when they received some of pyrite from a mine nearby, the Fallon mine, and they did this refining, they had left over this red precipitate. And that red precipitate they assumed was arsenic, actually. But when you heated it up, and here's where chemistry has changed a little bit, when you heated it up, it smelled like horseradish. You wouldn't do that today. That's why a lot of the original chemists died from their discoveries. But arsenic did not smell like horseradish when it was burned, so they had a clue that it wasn't or horseradish, but it wasn't arsenic. But it was. Garlic. Arsenic smells like garlic. I've never smelled arsenic either, but thank you for that. And I'm not likely to either. But the similar odor to tellurium told them it might be around the same group. So that was, it was discovered from that. They named it, now we had tellurium, which was named after the Earth, and selenium was named after, from the Greek selene, which means the moon, and so that comes down to us now as selenium. Selenium actually does occur naturally. You can actually find it natively. Here's a piece of native selenium. Here's another one. It's the purple part there. So it does occur naturally, but doesn't occur naturally in great enough quantities that you would mine it that way. It still has to be refined from things. There is, by the way, a mineral that's called selenite or selenite. That mineral is also known as satin spar, and or desert rose or gypsum. However, the thing about this is that there's actually no selenium in it. This is actually calcium sulfate. So, but it has a nice name that's related to our element tonight. Selenium is refined from the tailings of copper. So selenium really kind of starts with some of the same minerals that we find copper in, azurite or malachite, or actually you can actually find native copper laying around on the ground as well. But normally you don't find native copper. Again, not a commercially viable way to get copper. You have to take it and refine it. Usually electrolytically, you pull it from solution using charges. Here's a modern copper electrolysis apparatus. And so when you take the copper out of solution, you leave stuff behind. And in the tank that these copper electrodes were in, you build up a sludge at the bottom of the tank, and all that sludge is stuff that's not copper. And it's actually called anode slime. And then you can take that anode slime from the bottom of the tank here and further refine that, and so they get selenium this way. Selenium has a couple of different forms at room temperature and pressures. This is two different forms of selenium. These are called allotropes. And allotropes are really, they're both selenium, these are both pure selenium, and you can convert them to each other by heating them up and cooling them down in various ways. Red selenium, which I don't have a sample of, and gray or black selenium, those are they're both the same thing. They're both selenium. Solid pieces of selenium might look like this. It's not a very expensive element. It's recently kind of spiked in price. It was down in the 20s, and it's recently kind of spiked up to $65 a pound, but that's still not super expensive. It's used for a few different things. Most of the selenium is used in metallurgy, mainly for refining other metals. Most of the other is used for glass manufacturing. We're going to talk about some of this stuff. 10% for agriculture, 10% for chemicals and pigments. We'll talk about that too. A little bit in electronics and other uses, 5%. It's not a real common element. Here we see that as a proportion of elements in the universe, it's the 31st most abundant element in the universe. So it's not up there. It's not hydrogen, helium. It is, it's moderately rare. Not much of the universe, about 0.03% of the universe is selenium. Oddly, like I think we've seen this before, in the sun, there is no selenium. Where did it go to? I can't find a really good answer for that. I can only assume that in the synthesis of elements that happen within the sun, that selenium gets used somehow and used up. In meteorites, it actually has the highest abundance of anything in my charts here. It's actually the 25th most abundant elements in meteorites. In the Earth's crust, it's pretty rare. The 69th most abundant element in the Earth's crust, only 0.05%. But a lot of it has gone into the water of the ocean. So here we can see that in the oceans, it's actually quite a bit more abundant. It's the 35th most abundant element in the oceans. And last but not least, we have to think about us here in the human body. It's not super rare. You can see it's down there near the end. I mean, it's pretty rare. It's not super abundant, but you can see that it's about 0.05% of your body. And we'll talk a little bit more about that as well. Originally, although there's none in the sun, it's not made in our sun, it is made in stars. It's made in exploding supernova. So the fact that there's selenium on the Earth means that the Earth must be not a first-generation planet. It's made from the debris from exploded stars, as is, because actually you can see a lot of the elements there are made from the debris of former stars. I mentioned that selenium has 34 protons in the nucleus, but a variable number of neutrons. And things that have differing number of neutrons but the same number of protons are called isotopes. So there are 30 isotopes of selenium. That's a lot of isotopes. However, there's only 5 stable non-radioactive isotopes, and here they are. So selenium, now this number here is 74, and that's the total number of particles in the nucleus. So protons plus neutrons. Selenium 74, 76, 77, 78, and 80 are all the stable isotopes of selenium. So these are the ones you find in nature, but you find them in different proportions. Let's take a look at that. Now, another one kind of snuck in there that's in magenta down here. We'll get to that. So you can see that most of the selenium is selenium-80, and about a quarter of it is selenium-78, and less than 10% for all the other isotopes. This one here I kind of snuck in. Selenium-82 is not a stable isotope of selenium. It's radioactive. So let's take a look at, I just like to look at the isotopes that are radioactive but last a little longer than a minute. So there's a chance of actually seeing some of that stuff around. And you can see that these have half-lives from a few minutes to, well, this one here, selenium-79, has a half-life of 300,000 years. But selenium-82, remember that one that snuck in there under the stuff that's actually still found in nature? Notice it has a half-life of 10 to the 20th years, a 1 with 20 zeros after it. That's a lot of years, by the way. It's been around for a long time, and it's going to be around for a long time. As a matter of fact, after all of these elements have decayed and are gone, selenium-82 is still going to be there because it has a half-life that is very long. I mean, the universe is only, what, 13.8 billion years? So that would be like 10 to the 9th, 10 to the 10th years. So the universe is, the half-life of this is actually 7.25 billion times the age of the universe. It's not very radioactive. If you had a lump of it, you might even have a hard time detecting it was radioactive. So selenium is it's a non-metal, really. It's a metalloid. Here, I have some here in case you want to come up and see some after. This is what it looks like. If you can come up and see this, but don't take it out of the plastic bag because it's mildly toxic. So I would rather you not touch it, the element itself. But you'll be able to feel that it's kind of brittle. It's kind of almost glassy in nature. Actually, you can see some of the fractures here are conchoidal fractures, like you see glass break. It's kind of a middle density element. It has a density of a little less than 5 grams per cubic centimeter. Everybody knows what density is. It's how much stuff is in a given volume, right? What's the density of water? 1 gram for every cubic centimeter. Yeah, here's some other densities down here. So you can see that the density of selenium is a little denser than, iron's a little denser than selenium, lead's quite a bit denser. And I have over here, by the way, for those of you who haven't been here before, some blocks that are made out of different materials, starting with maple and plastic, and actually we can see those densities right here, ending in tungsten, which is the most dense element I have access to. So down here you can see tungsten and lead and copper and iron and titanium and aluminum and magnesium, and I don't have a block of selenium. But you can feel kind of the density from this bag. This is 100 grams of selenium. So I have a good range of densities if you want to play with the densities. Be careful if you lift up I have to warn you about the tungsten. It's extremely dense. So if you lift it up, both hands underneath, lift it with both hands, don't drop it on your foot. It will leave a mark. Gold is, by the way, this, in case you're interested, gold is the same density as tungsten. So lifting that brick of tungsten is the same thing as lifting the same size brick of gold. So you'll get a feel for what gold feels like. On the hardness scale, again, this is Mohs scale of hardness for you people who know your geology. 1 is one of the softest thing, like talc is one that you can scratch it with your fingernail, and 10 is diamond. Selenium is right there, so it's pretty soft, has a softness of about 2 on the Mohs scale. So about the same as sulfur, which we have seen before, and calcium we've seen before, but I couldn't take calcium out of the jar. Pretty soft element. This has an actually fairly low melting point. There it is, way down there. Its melting point is only 221 degrees C. So about twice as hot as boiling water. Yeah, you don't have to really heat this up very much to get it to melt. As tempting as it was to melt that into one block, I resisted the temptation, didn't want to kill myself. Boiling temperature is just a little bit higher. Boiling point is 685. So again, pretty low. We're not in the thousands of degrees like we are with metals, or like 6,000 degrees with tungsten. We know that tungsten has a high melting point because it's glowing white hot up here and still not melting in light bulbs, if you can still get tungsten light bulbs. Because we're approaching the end of the periodic table where the noble gases are, the electrons are being held closer and closer and closer to the nucleus, and so the selenium atom is actually fairly small. This is just comparing it to the hydrogen atom, and that will get even smaller as we progress on to krypton in 3 months. It has kind of a pretty spectrum, but not one that I can show you because I can't put it in a flame. But it has lines. Each one of these lines that you see here is uniquely made by selenium. So if you see that pattern in a spectrum, you know you have selenium. We can tell. It's a very useful tool in virtually all of the sciences. So what's it used for? We mentioned in metallurgy, it's used to refine metals. So one of the metals that it's really used to refine is manganese, one of those ones we've already hit, number 25. You use selenium compounds to purify manganese. And this is during the, again, manganese is separated using electrodes and from a solution. And when you add selenium dioxide to that solution, it kind of decreases the power necessary to plate the manganese out onto the electrodes. So it saves a lot of money. So China is the largest consumer of selenium and for this purpose. For every ton of manganese that you refine, you need about 2 kilograms of selenium dioxide. If you're going to make your fixtures in your bathroom or your kitchen out of brass, well, brass often has a lot of lead in it. So you would like to not have lead in your fixtures in your kitchen and your bathroom because you don't want to be drinking it. And so there is a way to make lead-free brass, and you substitute you substitute selenium for the lead. So you substitute a slightly less toxic material for a more toxic material, and you get lead-free brass out of it. That was actually kind of mandated by the Safe Drinking Water Act of 1974. It's actually marketed as something called EnviroBrass. I like marketing. You can also use selenium for photocells, for solar cells rather. This is a solar cell where you actually have to plate several layers of material, and those layers are copper, indium, gallium, and selenium. And you can plate them on very thin plastic pieces, which means you can make them bendable. This is not as efficient as your standard silicon photocell that you would find, for instance, on the roof of the Exploratorium right above our head. There are 5,874 solar panels that are generating power. Hopefully one of these days we're going to get to zero use of PG&E, but we're working on it. We're going to be net zero one of these days. Selenium can be used to convert power from sunlight into electricity directly. Another one of those big uses that you saw on that usage chart was glass manufacturing. If there's any iron impurities in glass, it kind of makes the glass greenish. And by adding selenium, usually as a selenium compound, it actually can change the color of glass and make it a little redder. So by adding a little selenium, you can cancel the green out and make clearer glass. Or if you want to go a little further, you can add even more selenium and use it as a red dye in your glass and make this beautiful colored glass using selenium. Or you can also use it as a glaze in pottery. So here's the red glaze there is selenium glaze. It's a really beautiful color. Super high tech. Let's go super high tech. This looks kind of ancient Greek, but let's go super high tech. If you can make very, very small particles, and I mean nanometer sized particles, billionths of a meter in diameter. They actually, when they're exposed to blue or ultraviolet light, will fluoresce. And the color that they fluoresce depends on the size of the particles, which means that you can tune the color of fluorescence. These little tiny particles are made out of either cadmium selenide or lead selenide. So there's selenium involved here. And these things are called quantum dots. I love that name. Inside of these vials here are liquid containing quantum dots. And in this one right here, the quantum dots are a little bit larger than the dots here. These are a little larger than the dots here. These are a little larger than the dots here. But you really can't tell until I light it up with ultraviolet light. So here's what happens when you light it up with ultraviolet light. Yes, it's the right protocol. These are glowing because of the very tiny particles. The particles in the red are about twice the size as the particles in the green there. Actually, I have a slide showing that. In case you couldn't see that from the back. Same thing, but isn't that beautiful? But the ability to be able to tune the color that it gives off just by manufacturing the little particles, the quantum dots, the correct size, is a really interesting technology. For instance, let me look at one more slide, technical slide. So here, you can, I can't point with an ultraviolet flashlight. There we go. So you can see here that the red here is being made with 6 nanometer sized particles, whereas the green is at about 2.5 nanometer particles. There's kind of a cyan color, which I don't have here, down to 2 nanometer particles. The fact that you can tune where the peak is by manufacturing these little dust motes, they're actually much smaller than dust motes, these little particles means that you can actually make a fluorescent thing that might be useful to you. For instance, there is if you're looking at the kind of displays like I'm looking at here, an LCD display, there's what? There's a white light, big panel that lights up white. There's a liquid crystal panel that has little dots in it that you can turn on and off. You can make them transparent or opaque, black. And then in front of that, there's an array of colored filters, red, green, and blue colored filters. Well, if you're just taking white light and you're filtering it with the filters are cutting out probably 90% of the light. You're not getting a lot of the light from here through the colored filters on the front. But if you could make the colors that the panel gives off, the white panel, specific to the filters, you get a lot more light through, and you can make things a lot more saturated. And there are now televisions, QLED televisions is the brand name for them, and that use a backlight of quantum dots that make just the proper red color, just the proper green color, just the proper blue color to get through the colored filters in the front. Much more efficient. Really cool technology. This was made by a company called Nanosys. They're just down in Mountain View. They make little tiny particles. The very first blue LEDs were zinc selenide LEDs. That has been supplanted now. Now they're gallium arsenide. That relates back to last month. But the very first blue LEDs were selenium based. If you're a photographer, well, you have to be a photographer, not a digital photographer. If you're like me, and I used to run a darkroom where we actually had solutions, you put the print in and everything. We had something called Selenium Toner. And Selenium Toner would take a black and white print, and you could kind of tone it. You could make it a different color. Here's an example. So take a black and white print, and you'd soak the paper in Selenium Toner, and then you would get something that might look like this, a kind of a sepia color. Although Selenium Toner would also do some other interesting things as well. It colors more than prints, though. If you have your selenium in the form of an acid, Selenous acid, H2SeO3, you actually can coat it on things like brass and aluminum, and you can kind of stain those things black, and that's for antiquing. Or you can also, there's a version of this also for steel. We use a lot of the steel version in the museum here to color the steel exhibits, parts of the exhibits black. Here's an example of the black coating that you get from those, from Selenium Acid on a watch and these mechanical parts here. One thing that you may have at home that has selenium in it, if you have dandruff shampoo, you ever wonder why it was called Selsun Blue? Selsun Blue has selenium in it. It's not because it doesn't have a Selsun motor. There's a kind of motor that's called a Selsun motor, but no. Selsun Blue has as the active ingredient, yes, selenium sulfide. That is the only active ingredient in dandruff shampoo, and it's selenium based. If you're an electronics person and you go back in time a little bit, you may recognize this device here. But you have to be a little older to recognize this. This is what would be called a diode nowadays. Back then, this is called a selenium rectifier. And those plates that you see have coatings of selenium on them. As a matter of fact, if you look at the diagram here, you can see there's cadmium selenide right there. And it meets up with an electrode of tin, and current here will flow in one direction but not the other direction. It's a diode. That's what diodes do. But this actually has another interesting quality to it, and that is if you try to send electricity through it backwards, it will not allow the electricity to go through backwards until you raise the voltage enough, and then it'll conduct backwards. So this is also useful and is still used in anti-surge. If you have an outlet strip that has a surge protector built in, it has a couple of these devices in it so that if the voltage builds up really high, they start conducting and they form a short. So the high voltage doesn't get to your electronics. It shorts out in the outlet strip and may burn out the outlet strip, but who cares? It protected your computer. Okay. One of the more interesting uses of selenium was discovered by this guy. I had to include him because I just love the name Willoughby. Willoughby Smith, he discovered that selenium changes how conductive it is depending on how much light is falling on it. That's actually a pretty cool thing because that means you could use it to measure how much light is hitting something. So for instance, in a device like this, again, for photographers who have been around a little while, you might recognize the good old Sekonic flash, the Sekonic light meter. And the Sekonic light meter has selenium-based photocells here, and that allows you to measure the amount of light hitting your subject or reflecting off your subject. Which gets us to one more really interesting application of photoconductivity and selenium. This guy, Chester Carlson, was playing around with trying to make copies of things. He was the first pirate. He was trying to make copies of things. But the ways you could make copies up to that time all involved a wet process where you had to get the paper wet. He wanted to make a dry process. And so he invented a process that was completely dry, but he needed a photosensitive surface that would discharge when light fell on it. And he chose selenium as one of his substances. You can use sulfur too, by the way, just pure sulfur. But he started out and invented this process, which we now call xerography, from xeros, meaning dry, and graphy, meaning writing. And his very first Xerox, of course they didn't call it Xerox back then, his very first xerographic copy was just the date and the place that he made the copy in. Surprisingly, that's what the first copy was. It wasn't a picture of his butt, so, you know. This, of course, made him quite wealthy. He was working for, he founded a company called the Haloid Company, which later got changed to Xerox. And it was such a success that he even had a stamp made of his likeness. Here is his first patent. By the way, you can look it up. And you may notice that if you read through the patent real carefully, you'll find that selenium is in there as the photosensitive surface. That led to the very first Xerox copiers, the office copier. This was a revolution. This thing could produce 7 copies a minute. 7 copies a minute. Yeah, it was a wonder. There's some really great commercials on there. Look up the Xerox commercials on YouTube. They're very humorous, and you can see how things have changed in the office since the commercial was made. Inside of that copier was, and really one of the revolutions of Xerox was that everything was done on a drum. So you could continuously turn the drum and make copies. There's the drum. The drum had a surface that was coated with selenium. This drum, everything happened on the drum. It was exposed. The toner particles were attracted to it. You put a piece of paper nearby. You attracted the toner particles away from the paper. It all happened around the drum. Very, very cool process. If you want to know more about this xerographic process, I highly recommend that you go on the web. Here's the web address. So if you want, I'll bring the slide up after. If you want, you can take a picture of it. This is a program that was made a long time ago by artist Tim Hunkin called The Secret Life of Machines. And he did 18 of them, telling you how different machines worked. This one, season 3, episode 6, the last one was the photocopier. And Tim, by the way, who is an artist in residence here as well, comes here almost every summer. Tim goes through the xerographic process and shows you exactly what happens inside that copier. It's a really wonderful process. It really is. I highly recommend this. Here's another place where you may have encountered selenium. If you've ever stood in front of an X-ray, one of these plates, holding onto the bars above, getting a chest X-ray, the sensors behind the plastic here are made out of selenium, the Xray sensors. Now, the selenium was actually about twice as sensitive as film, which meant that they could take the same X-ray with half the number half the amount of radiation. So this was a really nice breakthrough. In the human body, selenium is an element that you have about 13 to 20 milligrams of selenium inside your body. It's often given to you as a dietary supplement. You only take maybe 50 to 70 milligrams micrograms per day of selenium. So it's not a super abundant element in your body, but you do need it. It's toxic if you take it in large amounts. That's why I want to keep that in the plastic bag. But it's present in all animals. You even actually give it to, it's actually included in infant formula to make sure that infants are given the proper amount of, if you feed your baby, formula. And it's important in your thyroid gland. Almost every cell that uses any thyroid hormone uses selenium. You don't have to take it in supplements. If you want to take selenium in a natural form, one of the highest concentration selenium things you can eat are Brazil nuts, which, by the way, are not nuts, and for the most part are not grown in Brazil. Just FYI, they're mostly grown in Bolivia. But these have the highest known concentrations of selenium, and it's not because they need it, who knows. But this is one way that you can get your selenium. So we're sort of at the end here. So we're at our haiku stage here. So here's the haiku for today from Mary Soon Lee. So proud to be part of each drop of formula helping babies thrive. So next month, there will be no Everything Matters, Tales from the Periodic Table. We're going to skip January. But in February, we do have one coming up, and it will be bromine, element number 35, and that will be on February 21st. So we hope you'll come back for that. I also still have a couple of talks this month. If you're interested in full spectrum science, we have one coming up on mixing color. So if you're interested in why your primary school teacher lied to you when he or she told you that the primary colors were blue, red, and yellow, I'm going to tell you why. So I'm not going to tell you why now, though. So you'll have to come either this coming Sunday, 1 and 3, or next Thursday at 8. So thank you for coming, And if you have any questions, please come up and ask. Play with the density blocks. Come up and see the pure selenium. And hope you enjoyed tonight. Thank you.